Okay, come to here, then yes. Yesterday, I think I completed something related to what? Torque, angular momentum. Yeah, correct. Yes. One problem I think I gave yesterday. Got the answer for that question? Or else the same reason, busy with the project, mental project. Okay, right. Okay, even Amog is also not responding. Torque and angular momentum in parabola, right? Correct. Amog torque mgu cos theta into t, angular momentum mu into ut minus half gt square. Good morning, Sharma. Amog, I think you missed one basic concept here while doing that problem, what I gave yesterday. Sunil Kumar is there, Nana, in your class? Potkanuri P. Sunil Kumar. Is he there in your class? No. Then who is there? I think maybe his father's name or some. Okay, we'll try to. Okay, then here. Yeah. That's what I'm thinking. Okay, with the parents' mobile, I think. Yes, in the parabola, what we started the problem, solution for the problem here. Suppose you projected the body with an angle theta here, of course with a velocity u. After certain time, somewhere here or there, anywhere, somewhere, I'm asking what is the torque and angular momentum. Okay, torque is the force into perpendicular distance. Already you did it at the highest point. Okay, so using that simple knowledge, you can try it here. This is mg acting downwards, and here you can say very easily what will be the perpendicular distance about the point of projection, that is from point of projection. From point of projection, the perpendicular distance will be very simple, you can say. This is not half hour, Charnipriya. It is not at maximum height, na, somewhere. Okay. So somewhere means this kind displacement along x-axis. I don't know whether you remembered or not. We took it as x in the derivation, and vertical displacement we took it as y. Good morning, Deepak. Okay, that is u cos theta into t. Yes, no problem. Okay, so here torque you can write easily. Torque is equals to force into perpendicular distance, that is x. Not u square by 4g na? No problem, no problem. Okay, mg into x, that is mg into, here look at x. You already know in the motion in a plane chapter, that is u cos theta into t, horizontal displacement. Okay, so x is equals to, for reference, we are writing here u cos theta into t. And y also, I think you remembered, that is u sine theta into t minus half gt square. This is the y value. Yes, yes. So torque easily I got, that is mg into u cos theta into t, that is m u g t cos theta. That's it. This is the torque what I got here. Okay. If you want the vector form, you can write even in vector form also. Tau is equals to, in vector form, I write here. What we have to write, tau bar is equals to r bar cross f bar. I think you remember it. Okay. R bar, this is along x-axis. So R bar, I write it as xi cap by taking it as x-axis. And this one as y-axis, reference axis here. So xi cap cross, force is downwards, Nana. Downwards means it is along negative x-axis. Is it correct? Okay. So negative y-axis means, shall I write it as mg into minus j cap? Okay, Nana? Right. Then I write it as mgx, same magnitude I'm getting, mgx. But I cross j, I have to write k. So this is I cross minus j. Minus j means minus k. So now you say it is into or out the torque direction. I got minus k cap. Out means Lakshmi Gayatri, positive z axis kada. Yeah, outwards is positive z axis. Inwards is negative z axis. That's fine. Direction of torque, that is torque acts into the plane, into the board. Okay, inwards. So happily I can put the mark here, inwards. And keep in mind, if anyone asks the axis of rotation here, the direction of axis of rotation, then you can say axis of rotation is into, not outwards. Okay, you can say this is the direction of axis of rotation, inwards, negative z axis. Right, good. Thank you, Shan. Okay, right. This is the torque. Keep in mind, torque, angular momentum, everything always acts along the axis of rotation. Okay, that's why if you know the direction of torque, you will come to know the axis of rotation. Means the direction of axis of rotation. Okay, I think you got it very easily. Which one? The torque. But I think angular momentum not this much easier to solve. Okay, look at the angular momentum here. Again, I'm drawing the diagram. This is as usual, I'm taking x-axis and it has y-axis. Okay, and the body direction I'm taking here. This is the parabola. And somewhere here, he is asking the angular momentum. That one wisely we have to write. What's look at what will be the direction of r bar here. Okay, Look at, first of all, the linear momentum. Linear momentum means it is along the tangent. Oh, what happened? Along the tangent. Okay, tangentially acts. Tangentially, the linear momentum is mass into velocity. Okay, this is P bar. P bar equals to, while writing here, mass into velocity, V bar. Problem is, there the velocity is neither along x-axis nor along y-axis. So I don't know whether you remember this formula or not. Try to recollect from motion in a plane chapter, Vx I cap plus Vy j cap. Okay, that equals to, I write here, Vx is equals to, again try to recollect, that is u cos theta in motion in a plane chapter. And Vy is equals to u sin theta minus gt into j cap. Okay, what I substitute, correct, Nana? In place of Vx u cos theta, in place of Vy u sin theta minus gt. Is it correct? Yes, correct. Good. This is the linear momentum. Right. This is what I'm saying. Not that much easier. Okay. We are getting both the terms. Yeah. And here R bar, if you write position vector, thank you, Sharma. Position vector here, look at, it is from axis of rotation, the position vector I'm taking like this. Okay, this is the position vector. This is R bar. R bar can be written as in vector form, like the x I cap plus y j cap. Okay, so I'm coming back to here. This is R bar along x-axis x I cap, along y-axis y j cap. Okay, for the values of x and y, okay, wantedly already I wrote here the two equations. Okay, so better I write even Vx and Vy also here, so that while taking a reference, you can have a glance through these two equations. Okay, xi cap plus yj cap. X I am going to substitute as usual u cos theta into t I cap, plus y is u sin theta into t minus half gt square into j cap. Okay, now you have to take the cross product of those two, or cross t. Okay, now right here, r cross t, angular momentum. See here how much big terms we are going to get there. R u cos theta into u cos theta into mu cos theta. First you are getting I cross I. Anyone remembered I cross I value, Nana? 0. That's why this whole term becomes 0. Okay, we are not in the initial days of vectors, so no need to write this step. I cross I, straight away 0, so erased. Okay, next R cross P, second term I am multiplying. Okay, you will get I cross J. In the meanwhile, try to recollect, Nana, who is that I cross J? Yes, somehow K. Very good. So u cos theta into, you will get here k, that is correct. Not 1, k, right. U sin theta minus gt into I cross j, that is k cap. Okay, so product of u cos theta with the two terms over. I think I forgot m here. Thank you. Okay, right. Next, multiplication of this j into t, u cos theta into t. Oh, here I forgot one more term. Yes, u cos theta into t, and this is m into u sin theta minus gt. I think now I'm correct. Yes, all right. Next, I'm coming to the product of the second term with the 2. Okay, first plus u sin theta into t minus half gt square into mu cos theta into j cross I. This time I'm getting, Lakshmi Gayatri, this time quickly responded. Correct. Amount. That is minus k cap. Yes, yes, minus k cap. And this term, first term multiplication is over, second term multiplication, you will get j cross j. J cross j is 0. Right. This is minus k cap and that is 0. 0 means no need to, yes, no need to take it. That is 0. Okay, Nana? Good. Then coming back to here, next one, in the next page. Both I got k cap, Nana, keep in mind. That implies L bar equals to, I got there, here, by multiplying the terms, m into u cos theta into u sin theta. That is m u cos theta into u sin theta into t. Okay. And next one. This is m into u cos theta into t into gt. That is minus mu cos theta into t into gt. That is gt square. Okay. Correct, Nana? Any mistake here while multiplying the terms? No. Very good. Thank you. And second term multiplication. Right. Here it is minus k, Nana. So first multiply with minus u sin theta into mu cos theta into t minus u sin theta into mu cos theta into t. Okay. Next, minus of minus, that becomes plus. That is mu cos theta into half gt square. So plus mu cos theta into half gt square whole into k cap. Understood this one, Nana? And found any mistake in the multiplication? Yeah, no mistake. Thank you. Then straight away look at here. This term get cancelled. Half m. Oh, final answer. Okay, okay, right. You are right, Amok. Amok is saying the final answer after cancelling these two terms here. You will get the final answer as yes, mu cos theta into gt square, and this is minus mu cos theta into gt square. Same terms, if you take common, minus 1 plus half, minus 1 plus half is minus half. Yes, Sharma, thank you. Yeah, so you will get minus half mu cos theta minus mu cos theta into gt square, yes, into k cap. Okay, therefore the magnitude of angular momentum is along negative z axis. Magnitude is half mu cos theta into gt square. This is the magnitude of angular momentum, Nanamok. Now we understood the mistake what you committed. Right. Yes. Along negative. Yes, yes. Good. Minus k cap. Nana. Minus k cap gives the direction. Na? That's what I'm writing. Along negative z axis. Okay, Charmi Priya? Right. That minus k cap gives the direction. Right, good. So this is one model related to what? The angular momentum and torque. Okay. Of course, still many models are there that you have to practice. Without practicing, here mere waste of discussing the problems. So better once you go through the assignment, then we will discuss few more models. Okay. Right. Good. And now we come to here another concept. The torque and angular momentum are related as tau is equals to dl by dt. Anyone remember? Yes, yes. Rate of change of angular momentum. Okay. Now what I am saying, using simple mathematics, by differentiating whom you will get 0 there on the left hand side. By differentiating whom you will get 0 there constant. Very good. That's what I'm doing here. Suppose if tau is equals to 0, then here this L should be constant. Am I right? Means if L is constant, then tau equals to 0. Yes, yes. This is exactly identical to try to recollect. If force is equals to 0, then linear momentum is constant in translatory motion. Okay. It is identical to, it is analogous to F is equals to 0, then P is equals to constant. Then we stated it as law of conservation of linear momentum. If there is no external force, then the linear momentum is constant. In the same way, why don't you state it like if torque is equals to 0, angular momentum is constant? Okay, try to name it. It is called as law of conservation of angular momentum. Exactly. Law of conservation of angular momentum. Okay. Here. This is one law what we are getting here in this chapter. Law of conservation of angular momentum. No problem, Nanasri. Maybe I think signing in and taking more time there. Maybe. Yes, yes, it happens. That's what I said yesterday. Before joining, only better if you sign in, then directly you can join here. Okay. From tomorrow onwards, you do like. Yeah, yeah, good. Then there will be no problem. Right. This is the law of conservation of angular momentum. Right. This is very important when you come to this chapter, like law of conservation of linear momentum in that chapter. This is the important part here. Okay. So in the same way, LCLM, law of conservation of linear momentum, in a short form we discussed. Then the same thing, according to here we write LC. Is it LM in this chapter or AM? LCAM. Okay, right. Law of conservation of angular momentum, LCAM. I write L is equals to 0. Sorry, L is equals to constant if the external torque is 0. Better we write instead of if, since here. Then it is grammatically correct. Since external torque is 0. Okay. Angular momentum means for the bodies, try to write, usually we write what? Before the collision, the angular momentum is equals to after the collision, the angular momentum. In the same way, L before the body is coming in contact is equals to L after the body is coming in contact. I write the angular momentum concept. So before doing something is equals to after doing something. Okay. That implies angular momentum for a body, we can write R cross P, or else in terms of moment of inertia, we write it as I omega. So I can write it as I1 omega 1 before is equals to I2 omega 2 for a given body. Or you can write in another form also. What is the another form, sir? L is equals to constant. So for a given body, I write I omega equals to constant. That implies in the proportional form, I write it as I is inversely proportional to omega. Omega is taken to the other hand. This is another form. Okay, for a given body. Okay, so you can write that in two forms. Either I1 omega 1 is equals to I2 omega 2, first one, or you can write like I is inversely proportional to omega, since I omega is equals to constant. Okay, all right. This is the way. So where we use these equations and where we apply the law of conservation of angular momentum. Where to apply? No need to say. If there is no torque, there you can apply the law of conservation of angular momentum. Simple thing. But sir, that is very easy to understand, sir, but very hard to apply that in applications. Yes. L before is equals to L after if external torque is 0. That's what I'm saying, sir. So if external torque is 0, very easy it is. Yes. But when you come to apply it practically, okay, that is not so easy to understand. Okay, observe here what they ask. Like if you see one example, a person, like skating persons, okay, ice skating or with the skating wheels, okay, like ballet dancing, Nana, they dance also with the skating wheels. Okay, right here a person is skating on a surface at a skater. Okay, is better I write sliding on ice surface. Keep in mind there is no friction. That's why wantedly I'm saying ice surface. Yeah, you are right, Isha. Okay, right. On ice surface. With folding, sorry, better I say with stretched hands first. Means by stretching the hands, he is skating on the surface, means sliding on the ice surface. Okay, and now suddenly he folds. Okay, it is not partiality, like he or she. Okay, anyone. So better I write here he or she. Again, girls may ask, always you say he, sir. Okay, he or she folds the hands. Okay, means initially like this, stretched hands. Now the person folds the hands like this, fold. Okay, then what happens, you have to understand first. Then the thing you have to write in words in the dash. Okay, after seeing this example, we can't understand what is happening there and what physics law we have to apply here. Okay, but if you think wisely, you will get the idea. What, sir? He gave the information on ice surface. There is no friction. And that too, he is freely sliding on the surface. He is freely skating on the surface. Yeah, means no one is applying the force and there is no external torque on the person. Okay, that's why don't we use the law of conservation of angular momentum? If you get that idea, it will be very easy to understand. Okay, got the idea, Nana, all of you? Yes, Sharma. Okay. So here, when you come to solution, I write since external torque is 0, I write according to law of conservation of angular momentum, we write I omega equals to constant. Yes, I omega equals to constant. Problem is, first, when he stretches his hands, already we discussed, moment of inertia for the same body depends upon the mass distribution. When he stretches the hands here, stretches the hands, same mass, but distribution from the axis of rotation means perpendicular distance will be more. When he stretches the hands, perpendicular distance is more. Yes, who depends upon the perpendicular distance? The moment of inertia, not omega. So the moment of inertia depends upon perpendicular distance. Yes. That's why here in the first case, moment of inertia, I say more. Okay. So here I write when he stretches, he or she stretches the hands. That's what I'm saying, Amog. I, when he stretches the hands, is greater than I when he folds the hands. Exactly what you say. I'm going to say that point. Stretches the hands. The moment of inertia, MI, moment of inertia, is more. And it becomes less when he or she folds the hands. MI1 is greater than. MI1 is greater, Kadisha. Greater than MI2. Yes, it's not less than. Yeah. So when he folds the hands, mass is coming close to the axis. Yes, close to the axis means perpendicular distance will be less. Then moment of inertia will be less. Okay. So here, first time and second time, I think you observed, first time moment of inertia is more, second time moment of inertia is less. That is, I is decreased in the second case. Okay, now come back to here. I is inversely proportional to omega according to this equation. If I decreases, what happens to omega? Mass distribution is less, correct? Omega increases. That implies omega is increased. Omega increases, what happens, sir? Immediately when he or she folds the hands, they start spinning on the ice surface. They spin like this about their own axis. The same concept we apply in ballet dance also. Okay, if one person, male, holds the hand of female, okay, and the female, suppose, stretch the hand, then she tries to spin on the toe. All of you know about the ballet dancing. Okay, on the toe, rolls, even rolls, skating also same, correct, same concept. Okay, if you want to spin, immediately you have to decrease the mass distribution. Simple logic. Not only there, Nana, even in case of the diving, springboard diving, okay, diving from the springboard in Olympic Games. Yes, yes, even there also, Sharma, what you say? Okay, here, there also after jumping, before jumping, they try to stretch the hands. After jumping, they fold the hands in Olympic Games. Then before touching the water surface in the swimming pool, they make many number of somersaults in air. That is spin. Okay. By counting those number of somersaults, we can announce the winner. How many number of somersaults a person made before touching the water surface. Okay. There also he is applying the moment of inertia concept. Even in many dances in Telugu movies and English movies or Hindi movies, any movies we see, suddenly they fly in air and they spin in the air and they land somewhere on the other place, right? On another somewhere. I think you observe, able to recollect the things now. What I'm saying? Yeah, Balakrishna. Ayyo, papam. Yeah. Actually, Allu Arjun do such kind of aerobics. Okay, and Junior NTR they do in Telugu. Okay, in there in Hindi, Hrithik Roshan is the best dancer. No? Okay. Yes, yes. Okay, coming to here. There. It means these are all what I'm saying, the practical examples. Okay. Yeah, in movies it is due to train. Okay, maybe. Right. Right. Coming back to here. When I decreases, omega increases. When I increases, omega decreases. Simple how to decrease for a body or increase the moment of inertia of a body. Here I said one example, just by changing the mass distribution. Okay. Same thing. Okay, in exam, he asked one model like this manner. If it happens, okay, we have to appreciate. Okay, coming to practical thing due to global warming. Okay, what he says, the icebergs at the poles what is this, Nana? Satvika? Okay, right. Icebergs. Okay, no problem. I think you try to chart with someone. Okay, no problem. At the poles of Earth, I is inversely proportional to IA. Where I wrote? What is this, Sharma? Okay, right. At the poles, suppose melts. Okay, melt and flow to the equator. Okay, that flows, whatever the water form that flows to the equator. of Earth. Already Earth is not at rest, nana, that is rotating and spinning also about its own axis. Okay, about its own axis, it is spinning. So while spinning, already there is some rotatory motion, angular velocity for the Earth. Because of that angular velocity, we are counting 24 hours per day due to that spin only. Okay. Suppose the icebergs melt and flows to the equator of the Earth. Then what happens? What happens? Oh, sorry. To the duration of the day, of a day. Present, all of you know, 24 hours. If icebergs, all icebergs change, surely change. That's what I'm saying. Surely change. Okay. Then what happens to the duration of day? Means that it is increased or decreased. He asked in exam. This is actually one VSAQ. What happens to the duration of day? Think wisely. These are the positions of poles. Okay. And actually, we have two options there: increase or decrease. Few students put the increase and few other students put the decrease. I got both the answers here. Yeah, that's we are going to discuss Lakshmi Gayatri. Okay, changes. Okay, Ishan very smart. Changes, pakka. But increases or decreases, that's we are going to discuss. Okay, right. So when the icebergs are at the poles, they are very close to the axis, Nana. Means mass distribution is less. When that poles that comes to the equator region, look at the distribution is increased or decreased. Angular momentum remains constant, Nana. Why? Because there is no external torque on the Earth. So don't say angular momentum decreases or increases. Angular momentum remains constant. Amok. Okay, na? Yeah. 2 pi by omega Deepali, correct. First, what we are saying. Yeah, mass distribution increases. Yeah. Mass distribution. Why? Because that is coming far away from the axis, from poles to the equator. So mass distribution surely increases. Mass distribution increases means moment of inertia increases. Simply I put one arrow mark like this. Means increases. I increases. Means increases. Okay. I increases. Here there is no external torque. Same concept. Since tau equals to 0, I write L equals to constant. That is again, I is inversely proportional to omega. Yeah. I increases. That implies omega decreases. Yes. Yeah, correct. Omega decreases. But I'm asking the time period. Time period already Deepali put the formula T is equals to 2 pi by omega. If omega decreases, then what happens to time period? Time period increases. Yeah, that implies, okay, the time period is, yeah, more than 24 hours. What I'm saying is greater than, more than 24 hours per day. Then day increases. Okay. Yes, I think if you say this to Sharat sir, he may feel happy, so that he can increase the duration of class. Yeah, and he can take more number of classes to you all. No. Okay, okay, okay. Right. Shall I go to the pages and stop the classes here today? We'll go and melt some. Okay, right.